everyone. Now we saw the last exercise in homework 8, and this is precisely the same exercise in page 44. And here actually by the strictly positive endomorphism, symmetric endomorphism, what I wanted to mean is that the positive definite endomorphism, because this is not a real number or something like that, but I think it was clear from the section 4. So, okay, to show the existence of a symmetric positive definite endomorphism V, whose square is U, by the section 4 we may suppose that there exists an orthonormal basis which diagonalizes U. So that means let E be an orthonormal basis of R to the N that diagonalizes U. And I want to prove the existence by using the matrix representation. So we consider the matrix representation of U in base E and denoted by M. That's a symmetric, definite, and positive. And by corollary 4.18, we know that there exists an orthogonal matrix and the diagonal matrix D such that M can be written as multiplication, M can be expressed in terms of S and D. And by proposition 4.20, by part 2, we know that these diagonal entries are the eigenvalues and they are strictly bigger than 0. This is also easy to prove. This is also easy fact to prove. And having strictly positive eigenvalues allows us to define a matrix V with the same orthogonal matrix S and the diagonal matrix D prime, whose diagonal entries are the square roots of the eigenvalues, because this is positive, and we can easily verify V square is equal to M. And actually so far I again prove proposition 4.20 part 4, but this is a proof in terms of matrix representation. And the other thing we need to be sure to complete the solution is the uniqueness. So for this purpose, we suppose that there exists another positive definite symmetric matrix N such that whose square is equal to M. And we may consider M as Q transpose times T times Q with orthogonal matrix Q and the diagonal matrix T with the diagonal entries alpha j's. So, okay. From now on, first we want to observe if or not Q, it can be, considered different orthonormal bases. Q diagonalizes also M, and to see that, we simply observe the equation QM Q transpose. This is by the assumption we know that M is equal to N square. And let me denote this equation 2, and let me denote this equation 1. And yes, by 2 we know that this is equal to T square. So that means Q also diagonalizes M, and on the diagonal we will have the eigenvalues of M. So up to permutation of the columns of Q, actually this alpha square and the lambdas is going to be, say, alpha j squares, and the lambda j's will be the same. So that means without loss of generality, we may consider that they are given in the same order. And similarly by equation 2, we know that Qn Q transpose is equal to T, and by this setting we know that this is also equal to D prime, this diagonal matrix. So that means N can be written in terms of Q, D prime, and Q. I will denote it by 3. And yeah, we know that, again by the assumption, N square, and by the setting N, we know that it is equal to M, and by the assumption B square is equal to M. And by equations 1 and 3, we can write that S transpose ds is equal to Q transpose dQ. So by just multiplying the Q transpose inverse and the S inverse from the left and right hand side, we see that the matrix S times Q transpose commutes with a diagonal matrix D. And yeah, we know that D has, it is given in the question, U has distinct eigenvalues, so that means this D has, this diagonal matrix has distinct diagonal entries, and S Q transpose commutes with D. You can easily see that S Q transpose is also diagonal, but we don't know if it is identity or not. It's just diagonal. And since it is diagonal, it also commutes with another diagonal matrix, D prime. So again, a rearrangement of this last equation, we see that Q transpose D prime Q, actually the same matrix S transpose D prime and S. So actually by the third equation we know that this denotes N, and by the first equation we know that this denotes V. So that means that shows the uniqueness of such an endomorphism V. Okay, thanks for your attention, and if you have any questions, please don't hesitate to tell us, and take care. Bye-bye.